Today we are going to see the third problem on heat engine. It's the third model. There are only three models in heat engine problems. This is the third model problem. The heat engine receives 800 kilojoule of heat from the reservoir at 1000 Kelvin. A heat engine receives 800 kilojoule of heat from the reservoir at 1000 Kelvin and rejects 400 kilojoule at 400 Kelvin. If the surrounding is at 300 Kelvin, if the surrounding is at 300 Kelvin, calculate first law efficiency, second law efficiency, and relative efficiency. Now we can write the given data. So it is clearly mentioned as a heat engine problem. So draw the layout of heat engine, the source, sink, and heat engine. The heat engine will produce a work output. The source will supply the heat, and the heat engine will reject the heat. So Q1, Q2, W1, T1, T2. So this is common for all the problems. You want to write the given data which is given. So I have given the highest temperature is 1000 Kelvin, the highest temperature is T1, and the lowest temperature is T2. It is given as 400 Kelvin, and the heat supplied is given as 800 kilojoule. So 800 kilojoule, write in the form of joule. 1 kilo is equal to 10 power 3, 800 into 10 power 3 joule. And heat rejected rejects 400 kilojoule. The heat is rejected from the heat engine, which is 400 kilojoule. So 400 into 10 power 3 joule. To find what are the data we need to find is we need to find efficiency of heat engine, for first law of efficiency, and efficiency of heat engine based on second law, and relative efficiency. So first we will start with first law efficiency of heat engine. First law efficiency of heat engine is defined as work done by heat supplied, or can be written as work done by heat supplied can be written as work done is equal to heat supplied minus heat rejected. That is Q1 minus Q2 divided by Q1. So in the numerator we will be getting a Q1 and denominator will be getting a value of Q1. So Q1 by Q1 can be written as 1. 1 minus heat rejected by heat supplied. We know this value, work done is not known. So work done is not given in our data. So we need to find the value of work done, but heat supplied and heat rejected is given. So we can use the second equation. So heat rejected and heat supplied is given. So 1 minus Q2 by Q1 value substituted, you will getting a value of 50%. This is called first law efficiency of heat engine. The second law efficiency of heat engine can be described as, so efficiency of heat engine, actual heat engine efficiency, or first law efficiency of heat engine with respect to divided by Carnot heat engine or reversible heat engine. So actual heat engine is called irreversible heat engine, and Carnot engine is called as a reversible engine. When you take the ratio between these two, then it is called as second law efficiency. We already find the first law efficiency, that is called actual efficiency is 50%. We need to find the ideal efficiency, that is called Carnot efficiency or reversible efficiency, which is equal to 1 minus T2 by T1. So we already described that the efficiency of Carnot cycle depends only on temperature limit. So it is called 1 minus T2 by T1. Heat rejected is T2, supplied is called T1. We know the temperature limits are given in our question. So we can substitute the given data, you will be getting a value of 60%. So already we had described in the previous problem, always efficiency of Carnot engine is greater than all other engines. So Carnot engine is a standard reference engine. Only Carnot engine will have highest efficiency. It's a standard theoretical reference in thermodynamics, 60%. So where actual engine is 50%, Carnot efficiency is 60%. Then we call this engine, the new engine is called as feasible engine. Otherwise, suppose if the efficiency we are getting here is 60%, and Carnot engine is 60%, then it is called as reversible engine. Both are reversible engine. Suppose the first law efficiency is 70% and Carnot engine is 60%. Actual engine is having 70 and it is having 60, which is highly impossible. So irreversible engine will not give highest efficiency. So then it is called as an impossible case. It is not feasible. So now the second law efficiency is described as actual efficiency by Carnot efficiency. We know both the value 50%, 60%. 50 by 60 will be getting a value of 83%. percentage. So next, the third one is called relative efficiency. When you take a relation between first law efficiency and second law efficiency, the ratio between first law efficiency and second law efficiency is called as relative efficiency. First law efficiency is 50 percentage, second law efficiency is 83 percentage. When you take this value, you will be getting a 60 percentage. This is called relative efficiency. So thank you.